So next, we are very excited to welcome Dr. Chris Miller to the Summit stage. Dr. Miller is a professor at the Fletcher School at Tufts University and is a non-resident fellow at the American Enterprise Institute, a think tank in Washington, D.C. He has an MA and PhD in history from Yale University and a BA in history from Harvard. His latest book, Chip War, The Fight for the World's Most Critical Technology, highlights how semiconductor technology underpins global power dynamics and shapes the balance of influence among nations, particularly among the United States and China. He argues that control over the design and manufacturing of microchips and the complex supply chains behind them will determine the economic and political future of the 21st century. The book is a New York Times bestseller and winner of the Financial Times Business Book of the Year Award, the Council on Foreign Relations Arthur Ross Book Award, and the Institute of Electrical and Electronics Engineers 2024 History Prize. At the conclusion of his presentation, Dr. Miller has graciously agreed to also participate in a fireside chat that will be led by Dr. Douglas Adams. Doug is the Executive Director for the Vanderbilt Institute of National Security and is also a distinguished professor of civil and environmental engineering, as well as a professor of mechanical engineering. Now, please join me in welcoming Dr. Chris Miller.
Thank you. Well, what I'd like to do over the next half an hour or so is set out how exactly we make artificial intelligence systems, the implications of the supply chain and production process for AI on national security, and why we need to think about our electronic supply chains more broadly, not just the chips that go in our computers or our smartphones or our data centers, but how those devices are in turn produced. Because it's not only the United States that's asking these questions. There's a competition internationally with the US and China in the lead, both to develop the most advanced AI systems, to deploy them widely across society and economy and government, and to wield advantages that each side has for political and security purposes. And so to start, I thought I would do what I always do now, which is ask ChatGPT, how is it that we create AI systems? And it gave me an answer that is true but incomplete. It started telling me about transformer architectures and algorithmic improvements and all the data that it was trained on. And that's right in a sense, but it misses perhaps the most important ingredient of progress over the past, not just couple of years, but couple of decades. And that ingredient is more and more computing power. If you look at the past several years and the current artificial intelligence boom, as well as the past several decades, what you find is that the most advanced AI systems of their day are trained on a rapidly growing amount of data, which requires a rapidly growing amount of computing power to undertake that training. Here's a chart of the most advanced AI systems from the 1950s, when the phrase artificial intelligence was first invented, all the way up to the present day. And you'll notice two things. First, it's always increased at an exponential growth rate. There's a logarithmic scale on the vertical axis. Second, the rate of increase hockey sticked upwards around 15 years ago when we entered the deep learning era. In other words, most of the advances that have delivered us better and better AI systems have come not from the algorithms that ChatGPT will tell you about, but from the computing power that enables bigger and bigger training runs, more and more computing undergirding it. This is true if you look at the biggest and best AI systems of their day. It's also true if you look at academic studies of drivers of AI progress over the past 15 years. Some of the best researchers who have tried to decompose what share of advances are due to algorithmic efficiency versus what share are due to just pushing more computing capabilities through AI systems found that there's a vast increase in the amount of computing that vastly outweighs the importance of better algorithms. Doesn't mean that we're not getting better algorithms or getting more efficient over time. We certainly are. But when you think of this scaling up of efficiency versus the scaling up of computing power, the computing wins, hands down. And don't trust me. Trust Sam. Just 2 weeks ago, he was tweeting his apologies to ChatGPT users that he didn't have enough GPUs, the ultra-specialized AI chips that are needed to train and to deploy AI systems. And this is not the first time he's publicly tweeted his apologies. Every couple of months, he's got a new tweet. I have to update my slides because his deficit of GPUs has been ongoing since ChatGPT was first released in November of 2022, and he's not alone. The entire US tech sector, the entire world has faced a deficit of computing power as we've tried to build and deploy bigger and better systems for chatbots, for image generation, for video models, perhaps down the road for robotics as well. It's this scaling of computing that has enabled the advances we've seen over the past couple of years. But in fact, the scale up of computing has deep roots, not just in the civilian sector, in the chatbots and search engines and recommendation algorithms that show us pictures on Instagram. The origins of modern computing is in the defense sector, in the effort to guide weapons like these more accurately. The first chips that were invented were used in the guidance computers on top of intercontinental ballistic missiles during the earliest days of the Cold War. The first large order for semiconductors after the technology was invented in the late 1950s was for the guidance computer that guided the Apollo spacecraft to the moon. The second large order was for this guidance computer that would guide Minuteman II intercontinental ballistic missiles from North America all the way to the Soviet Union. And since that day, there's been a deep interconnection between the needs of the defense industrial base and the national security community and advances in computing capabilities. All the way back to the origins of the industry, there's been a national security imperative at the center. And there's no organization that has benefited more from improvements in computing than the US military, which has managed to deploy computing not just to guide weapon systems, but to build constellations of satellites that can tell you your location or sift through vast quantities of sensor data or break into the most complicated encryption algorithms. All that is a problem fundamentally about computing power, and the harnessing of vast quantities of compute has been key to US defense strategy since the Cold War. The US has always known it's a large country with a large economy, but far less than half of global GDP. During the Soviet threat in the 1960s and 70s and 80s, it was understood by everyone that the Soviets had more tanks, more trucks, more missiles, more soldiers ready to fight in Eastern Europe. And so the US bet then that its only durable advantage was not in numbers, or at least not in numbers of things, but in strings of ones and zeros that could be deployed for different use cases, making better sensors, having better data processing systems, having better guidance systems. And the US has had advantages in nearly all of these spheres because of its embrace of computing power, because it had led the world in developing new capabilities, all the way up to the present day. And today, it's not futuristic to say that the cutting edge of national security requires artificial intelligence. Just listen to senior leaders. Here's the director of the National Geospatial Intelligence Agency in a talk late last year. AI is already happening. It's already being deployed to sift through data, to understand images, and to help make faster decisions. This is not a futuristic dynamic. This is already present in intelligence, in guidance, in increasingly autonomous systems are already deploying artificial intelligence, and the amount of computing power they can harness, both energy-efficient computing power on devices and vast computing capabilities like those that are wielded by the US intelligence agencies are key to their success. Which raises the question, well, how do we do it? How is all this computing power produced? And the answer is devices like these. Here's an NVIDIA GPU, the chip that Sam Altman can't get enough of, the core processor undergirding almost all of our advances in artificial intelligence, not just over the past couple of years, but really over the past decade. NVIDIA produces around 90% of the AI accelerators that undergird advances in artificial intelligence, whether at Meta or Microsoft or OpenAI or ByteDance in China or Alibaba. They're all relying on the same rough sets of chips with NVIDIA at the center. And chips like these are among the most complicated devices that humans have ever made, which means that understanding their supply chains is key to both guaranteeing we've got ongoing access to the quantity that we require and also key to making sure that our adversaries can't compromise the supply that we need. A cutting-edge NVIDIA chip could have tens or even hundreds of billions of tiny devices called transistors etched into their silicon. A transistor is a switch. It turns a circuit on or off, on or off. When it's on, it's a 1. When it's off, it's a 0. All of the ones and zeros undergirded computing. All of the ones and zeros training AI systems. All of the ones and zeros coding the Instagram pictures that you're sending to your friends are produced by circuits turning on and off. And if you want a lot of computing power, you need a lot of circuits, which means that you need to make them as small as possible to fit as many of them on a piece of silicon as you can. And today, the tiny circuitry in your smartphone or in a PC or in data center chips like these are not just microscopic, they're almost atomic in size. The most advanced transistors, like those inside your smartphone, are smaller than the size of a coronavirus. And you walk around with 20 billion of them in your pocket almost every single minute of the day. And as you can imagine, producing 20 billion coronavirus-sized devices is not easy. In fact, it's not just hard, it's the hardest things humans have ever done. What else have you bought 20 billion of? At a price point that was small enough that you can replace every couple of years. Nothing else comes remotely close. And it's only been possible to do because we've constructed some of the most complex supply chains in human history to bring together expertise from Europe and Japan and North America and Korea and perhaps above all, Taiwan, to assemble and design and fabricate chips at this extraordinary level of precision. Supply chains that are so complicated, no one, not a single company, not a single country can make an advanced chip on their own. Only decades of international cooperation have made this possible. And understanding these supply chains is, I think, key to understanding a good portion of the structure of the world economy today, as well as the balance of technological power. So let me walk you through, if I can, the semiconductor supply chain. And if you're someone who naturally falls asleep when someone uses the word supply chain, please give me 30 seconds of your time, and I promise I'll make it useful. There's a number of key steps required in making an advanced chip. First, you've got to access ultra-specialized software that will lay out where each of the 20 billion transistors on your smartphone processor is supposed to get. That's called EDA software. And there's only three companies in the world that make it. They're all based in the United States. Then you need to borrow or buy intellectual property from some of the companies that specialize in certain types of capabilities and will sell you the IP for that purpose. Almost all of that is in the US or in a UK company called ARM. Then you need to buy materials like silicon wafers, and not just any silicon wafers that are purified to the 99.9999999th degree. Because if you're carving transistors that are half the size of a virus, misplacing a couple of atoms can cause defects on your devices. And so although silicon is one of the most widely dispersed elements in the Earth's crust, the number of companies that can refine it to the level of purity is very small. They're mostly based in Japan. And all of the other materials, chemicals, explosive gases that are needed in the chip-making process require comparable levels of purity, with often just a single set of companies or one company capable of undertaking the requisite purification. Then you need the tools that are capable of producing transistors at virus-sized scale. And as you can imagine, these are the most complicated, expensive, and precise machine tools that have ever been made. You need tools that can lay down thin films of materials as thin as 4 atoms thick with basically perfect precision. Tools that can etch tiny canyons in silicon, roughly the same dimensions wide. And the most important of the tools that can pattern where each of the 10 or 20 or 100 billion transistors ought to go in exactly the right location with hardly any room for error, and do it fast enough to make mass manufacturing actually possible. More on these tools in a second. But it's key to note that once you've got these tools and the materials and the design and the software, you still haven't done any manufacturing. And none of the companies that design chips, nor design the software, nor make the silicon wafers, nor make the tools that make chips know anything about making chips. They don't make any. They outsource that entire process to companies that specialize in nothing more than assembling all of these different capabilities and actually undertaking the manufacturing at nanometer level precision. And today there's one company in the world, Taiwan's TSMC, that can manufacture cutting-edge processors far better than anyone. 90% of the world's most advanced chips, the chips in your phone, the chips in your PC, the chips in data centers, the chips in the telecom system, are manufactured by TSMC in Taiwan. 99%, according to a company executive last year, of the world's AI accelerators are manufactured by TSMC in Taiwan. Nobody knows where that other 1% comes from. I think he might have rounded down rather than rounded up. So the fabrication of chips itself is an extraordinarily specialized process with, again, huge concentration of expertise. These are the steps of the semiconductor supply chain. Each one has dynamics of oligopolies or even monopolization, where there's one country or one company that has unique capabilities that no one else can master, which is why you need a alliance, a cooperative agreement between the United States, Europe, Japan, Taiwan, and Korea to produce the most cutting-edge chips. And the surprise when you lay this out is the one country that's listed here that I didn't mention. The world's largest manufacturing superpower, the workshop of the world, the country that produces 37% of global manufacturing output compared to less than 15% for the United States. That's China. China uses an inordinate number of chips. It uses chips when it produces iPhones or dishwashers or servers or cars. But it imports most of those chips from abroad, from the United States, from Japan, from Europe, from Korea, and above all, from Taiwan. China imports so many chips that it spends more money each year importing chips than it spends importing oil. There's no more flow of goods in all of global trade larger than the flow of chips into China every single year. And if you were sitting in Beijing or in Shanghai or in Shenzhen, you could understand why that would make China nervous. It's their number one point of reliance on the outside world. They don't rely on just any country. They rely above all on Taiwan, an island that we consider autonomous and they consider a renegade province. So both for purposes of artificial intelligence, where better and better chips at larger and larger scale are centrally important, and for understanding China's economic relationship with the outside world, including Taiwan, semiconductors must be at the center of your analysis. And for a long time, this wasn't the case. Governments mostly ignored semiconductors. 10 years ago, if you went to Washington, you could barely find anyone who could pronounce the word semiconductor. Companies themselves found it easier just to ignore government because there was free trade in chips. China was a small player. They could compete with their commercial rivals, and everyone was doing well as we bought more and more electronic products with more and more chips inside. But that began to change about a decade ago when China targeted semiconductors as one of the key focus areas of its Made in China 2025 industrial upgrading strategy. In 2014, China set up its first national fund for investing in an indigenous chip industry, putting on $50 billion. That's more than the amount of incentives in the US CHIPS Act into China's own national level industrial subsidies. And the provinces and the municipalities followed behind with their own industrial subsidy funds. And so we've seen China's chip industry grow substantially over the past decade, from a very small base to still a small position, though increasingly important. But China still can't produce the most advanced semiconductors. The chips in smartphones, the chips in PCs, the chips in data centers, China produces only small volumes of them, and with capabilities that are still less than those that can be manufactured in Taiwan. And the primary reason is tools like this. This is one of the tools that you need to make advanced semiconductors. It's called an extreme ultraviolet photolithography machine. We'll do a quiz at the end. Who can pronounce that correctly? Say it 5 times fast. Until recently, you couldn't find a single world leader who could say extreme ultraviolet photolithography. Even the short version, lithography, was hard enough. But now when Xi Jinping meets with Dutch Premier Mark Rutte, as he did last year, and that's where these tools are made in the Netherlands, lithography machines are on the agenda. Because as of 2018, the Dutch government, under US pressure, has declined to give ASML, the company that produces these tools, a license to sell to China. And it just so happens that for now, without these tools, you can't make cutting-edge chips in an economically viable fashion at scale. And so you might ask, well, why doesn't China make their own extreme ultraviolet lithography tools? And the answer is because it is the hardest thing that humans have ever made. A single new tool costs $350 million a piece, not a small sum of money, has hundreds of thousands of components inside, including the flattest mirrors humans have ever made, the most powerful laser ever deployed in a commercial device, an explosion happening constantly as a tiny ball of tin, 30 microns wide, is pulverized twice by the laser, explodes into a plasma. The plasma emits light at just the right wavelength, 13.5 nanometers, to reflect off the world's flattest mirrors. The plasma itself measures 40 times hotter than the surface of the sun, yet the machine can contain this extraordinary explosion and direct the rays of light in just the right way to bounce off the mirrors and land on a silicon wafer to carve all of the 20 billion transistors inside of your smartphone. You can start to understand why this tool took around 3 decades to produce, involving the smartest scientists, most brilliant engineers from the United States, from Europe, and from Japan. You can also understand why no one else, at least no one else commercially minded, is trying to replicate this tool, because it would cost you an extraordinary sum of money. You might well fail, and if you succeeded, you'd still be behind, because ASML invented these tools a decade ago. And so the challenge China faces is to replicate not just this tool, but many others that are used in precision manufacturing, without which cutting-edge chips are basically impossible to make at scale. Which makes the question of Taiwan even more challenging. Because until around 2020, if you were a Chinese firm, you could contract with TSMC in Taiwan and have them make whatever chip you wanted at whatever advanced process you'd like. Then the United States government told TSMC to stop it, stop selling cutting-edge chips to China. First, AI chips, now increasingly many types of cutting-edge chips are no longer allowed to sell. And so China's now unable to produce the most advanced chips at home, looking across the strait at a region it considers a renegade province, where the United States is able to dictate to the largest company on the island to whom it can and cannot sell. I understand why that, too, would make Chinese policymakers pretty unhappy. And yet when it comes to the types of processor chips, the second bar right here, that TSMC specializes in, there really isn't much competition at all. A little bit of capability at Samsung of South Korea, a little bit of capability at Intel of the United States, but the bulk of the market, including almost all of the AI market, in Taiwan. Never before, I think, if we had an industrial revolution, a technological revolution predicated not just on one country or even one company, but 2 factories. And yet today it's the case that all of the GPUs that Sam Altman is struggling to get his hands on come from an extraordinarily concentrated supply chain, where concentration has given us enormous efficiencies, huge economies of scale, extraordinary, exquisite technological capabilities, but also staggering vulnerability. And it's not just in the chip making, it's in everything that goes around the chip too. If you want to take an AI chip and put it into an AI server, you need very complicated packaging capabilities that can manage the heat dissipation. And these chips have so much power going through them, they throw off an extraordinary amount of heat. You need precision manufacturing to bring the chip as close as possible to the memory unit. And almost all of this supply chain, not just the manufacturing of the chip, but everything around it today happens in Taiwan by Taiwanese companies. And so it's not as simple as saying, let's bring this process somewhere outside of Taiwan. You need to bring the entire supply chain somewhere else if you'd like some diversification. And the supply chain is by far the largest component of Taiwan's economy. So there's a very complicated dynamic in US-Taiwan relations when the US says, let's diversify. Taiwan hears, let's move offshore, our most important business. And yet, I think, and I'm sure Sam said something similar this morning, AI is not something in the future. It's something that's already happening. We're already dealing with more and more increasingly autonomous systems, both in the physical world and in the digital world. Look at the automotive industry. A dramatic growth in chip content over the past couple of years, and much more growth projected in the very short term for chips used in autonomous driving systems. Now, it's true we were promised flying cars decades ago and haven't gotten them yet. But I would posit that if you consider the extent to which a new car, especially at the higher end of the market, can increasingly drive itself autonomously in most cases, it's been a pretty extraordinary rate of increase. And all that's required a ton of additional silicon. In a new car, for example, you'll often have 1,000 chips inside. Some very simple, like moving windshield wipers back and forth. Some pretty complicated, like understanding all of the optical data that the car's cameras are taking in and making sense of that data and deciding whether to turn left or to turn right. This is already happening. This is already in our manufacturing supply chains, which means access to the silicon that undergirds it is not a question for the future, it's a question for today, as car companies learned much to their loss during the pandemic. And what's more, the price of artificial intelligence is collapsing, which is a very good thing for all of us who want to use more of it. We've seen dramatic price declines just over the past couple of years in the most advanced models, price declines that you've never seen in any other segment of the economy. And when prices decline, you use more of it. And if you want to use more of it, you're going to need more silicon optimized for artificial intelligence. And it's not just Sam Altman that's reporting that a deficit of high-end chips is slowing down its technological progress. Listen to the CEO of DeepSeek, a company that many of you probably heard about earlier this year, one of China's leading AI players. Since China can't import the most advanced AI chips, DeepSeek has had to scramble to get access to slightly lower-end NVIDIA chips. It had to rewrite a lot of the base-level software to overcome challenges of not having access to the most advanced hardware. And the CEO of DeepSeek has repeatedly said, including, interestingly, at a meeting in January with Li Qiang, the #2 Chinese government leader, that his #1 problem was not capital, not know-how, but access to advanced semiconductors. And he said it multiple times, so I don't think he's lying. And the challenge that China faces is that it's just not easy to ramp up production of AI chips domestically. If you don't have the advanced tools, you can't produce, at least not right now, in the way anyone knows, at volume. And so if you read the news, you'll find that the manufacturing yield of China's largest chip maker is around 20 or maybe 40%. In other words, the majority of the chips that they produce, 80%, don't work. Well, try ramping up volumes if 4 to 5 chips malfunction. That's why the leading Chinese chip makers have promised and then failed to deliver orders for AI chips to leading Chinese tech companies. It's also why, whether it's DeepSeek or ByteDance, which arguably is the leading Chinese firm when it comes to AI, are spending most of their procurement dollars not buying chips from domestic players like Huawei or Cambricon or others. They're spending most of their money building AI data centers full of downgraded NVIDIA chips that are still legal to sell into China. Imagine that. They know they could be cut off at any moment. They know they don't have access to the best NVIDIA, only to the second tier. And nevertheless, they're pouring billions of dollars each into buying this second-rate tech hardware, which at any moment might be frozen by the whim of the US president. That is a vulnerable position to be in, and yet there's no, right now, alternative. NVIDIA was estimated to have made $12 billion last year selling these downgraded GPUs into China. They're still pretty capable chips. I don't want to downplay their importance. There's a big debate right now in Washington whether they too should be restricted. But it's a pretty striking decision if you're going to bet your AI future on second-tier semiconductors. So when it comes to the most advanced computing capabilities, I still think that the United States, along with our friends in the Netherlands and Japan and Taiwan, which are necessary partners for actually manufacturing these chips, is in a pretty strong position so long as nothing goes wrong in the Taiwan Straits. Minor caveat. But we also don't think enough, I believe, about the lower-end chips that are, if anything, even more prevalent in the electronics that we take advantage of. Go back to a car and think of your semi-autonomous driving capabilities in a car. Cars increasingly have cameras, audio sensors, LiDAR sensors, communications capabilities. All that requires semiconductors. That's why you need 1,000 chips in a car, and most of them are not at the high end. You need a couple of high-end processors for your entertainment or your autonomous driving capabilities, but you need a lot of lower-end capabilities for your sensors and your communications capabilities. The same is true in a phone. Your primary processor in your phone must be manufactured with some of the most cutting-edge capabilities, but much of what's around the phone is lagging edge. And over the last couple of years, the United States and its friends in Taiwan and Japan and Europe have collectively decided to let China play a bigger and bigger role in the lagging edge of the market, on the, I think, false assumption that the lagging edge doesn't much matter. Lagging, it sounds old. It sounds like we don't need it anymore. But in fact, the more autonomous systems we build, the more advanced AI becomes, the more sensors you need, the more sophisticated systems you build, and the more lagging edge semiconductors you need in addition to the cutting edge processors. And so we've become increasingly reliant on lower-end Chinese semiconductors over the past couple of years, even as we've retained our edge at the high end. And China's pouring more money in. You've probably heard about the CHIPS Act in the United States. Well, China's been doing a CHIPS Act every single year. And most of that money is going into the lagging-edge semiconductors, where China already has the technological capabilities to produce high-quality chips. They're increasingly finding their way into our supply chains, into our cars, into our telecoms network, even, I think, into our defense industrial base, which raises some serious questions, some serious challenges. I think Hezbollah learned to its disadvantage last year how important supply chain security actually is. And while I don't worry about my iPhone blowing up, I think we should be cognizant of the cybersecurity vulnerabilities that having much of our offshore assembly located in a strategic adversary, in China. This is one of my favorite studies from last year. A Norwegian cybersecurity researcher did a teardown of his new Chinese-made electric vehicle. He found that 90% of the communications leaving the vehicle, the camera taking pictures of the road, the audio sensor listening for him to say, "Call mom," 90% of that data transited servers in China after it left his car. Pretty extraordinary number when you think of all of the devices that are watching and listening and gathering data and thinking for us, which to a very large degree are assembled with many of the components made in China. So what does all this mean for the defense industrial base? Well, there's clearly an imperative, I think, to stay ahead when it comes to the most advanced computing capabilities. Clearly an imperative to make sure we're deploying these capabilities as rapidly as possible, so our advantages don't just sit in the lab, they're actually out in the field. It's critically important to take supply chain security much more seriously than we have before. But the challenge the national security apparatus faces is that, unlike in the early days of the Cold War, when most chips were being bought for missile system guidance computers, today the Pentagon is a small buyer of chips. 1 or 2% of all chips sold end up in defense or aerospace applications. Mobile phones are a quarter of the market. And so it's not an exaggeration, I don't think, to say that Apple CEO Tim Cook has even more influence than Donald Trump over the shape of the chip supply chain. He buys more chips than anyone every single year. He's been the largest customer of TSMC every year for nearly the past decade. And so government has to work alongside the private sector and try to shape how the private sector buys, because the number of chips and the dollar value of chips bought by the public sector is just too small to really matter. What's more, the cost of production and the economies of scale that are required grow every single year. A single new cutting-edge chip plant costs twice as much as a new aircraft carrier. So you can understand why the Pentagon decided several decades ago now to outsource chip production to the private sector. There was just no way to keep up with the need to build a new chip plant every couple of years. And that was probably the right choice, in the sense that it enabled us to take advantage of the best technologies that the private sector was producing. But it also meant that we're reliant on a technology roadmap and a supply chain that is dictated first and foremost by the private sector. A private sector that for the past 3 decades has emphasized efficiency, not resilience, and therefore put its entire fate, its entire future, its entire manufacturing base on a single island right off of China's coast. Which means that all of the AI systems we'd like to build, all of the chatbots, all of the autonomous systems, all of the robots, all of the healthcare applications depend on peace in the Taiwan Straits, because no one else is going to replicate Taiwan's capabilities anytime soon. Not China, not, I'm afraid, the United States. And so at the center of the chip war, there's a competition between the US and China to produce the best chips. But there's also a strange and very uncomfortable interdependence, because we're both reliant on Taiwan to produce the most advanced chips that we can acquire, which is not a place that I'd like to be, but it's the place that we are. And it means that if you want to understand the future of AI, you should think about everything that Sam Altman described this morning, but also think about the supply chain too, because the shape of the supply chain and the security of the supply chain will dictate the future of AI in ways that we probably wish were not true, but I'm afraid will have very high impact over the coming years. Thank you very much for having me.
Thanks. Chris, thank you. That was outstanding, absolutely, and thanks for being here. You covered so much. So you have a room full of national security professionals. They've come here to discuss the biggest challenges facing the nation, facing the globe when it comes to security. What do they need to know? You know, what keeps you up at night? You've got their undivided attention. What do you want to share?
Well, you can probably guess that the Taiwan question keeps me up at night. But that's a question that's easy to worry about and hard to solve. I think the challenge that's easier to solve is our supply chain reliance on China, which, despite a decade of talking about it, the reality is that both for critical civilian infrastructure as well as for the defense industrial base, we haven't done nearly enough to extricate ourselves from production in China. And we haven't done enough to reduce our reliance on East Asia in general. If you think about the entire electronic supply chain, the chips, the printed circuit boards that they're assembled on, the capacitors, the resistors, all the things that are inside your phones and inside of electronic systems, almost all of that is made in Asia. A tiny, tiny fraction can be produced in the Western Hemisphere, usually at quality levels that are worse than Asia, with some of the most advanced capabilities impossible to produce today in the United States. And so I don't think we're going to resolve the cutting edge chip issue overnight, but I think it's not nearly as hard to start making progress on the rest of the supply chain. And that's where we haven't been as focused, and we should spend more time.
So I want to riff off of that for a second. So one thing you spent a lot of time on, and it was a fascinating description that you gave of the equipment that is able to, you know, using the most powerful lasers harnessed in a commercial manufacturing process, cut those very small transistors into the silicon. So I'm at a university. I'm thinking about all the folks that we're training in next generation manufacturing. You know, yes, it's challenging to build a manufacturing process and a piece of equipment that achieves that, but who is it that embodies that knowledge? Where is that corporate memory living? Are we capturing that? Because it seems like that's at least a piece of sort of staying in the lead when it comes to not just semiconductors, but AI.
You know, I think there's a really complicated relationship between universities and companies in the industry. There's no doubt that universities play a really critical role in a lot of the basic research that undergirds advantages. But I think it's also the case that the key know-how, the secret sauce, is not at universities. It's at TSMC, it's at ASML, because it's not theoretical knowledge. It's the empirical knowledge you learn when you've already built 10 of these tools and are working on your 11th. And what's more, it's often not even written down. And we know that because China's hacked all these companies left and right. Every document, one must assume, is currently on a server in China. It hasn't worked yet. It hasn't worked because the know-how is in the brains of the engineers. It's in the R&D organization itself, much more than it is on any sort of file or document in a company system.
That makes sense. Matt Pottinger, former Deputy National Security Advisor, wrote an op-ed. You and I were talking about this earlier in the week, back in January. Talked about the strategy for U.S. to stay competitive in AI involves investment in R&D, but also tight export controls. So, you know, then DeepSeek burst onto the scene right after that article appeared. Can you talk about how you think about the right combination of proprietary architectures, export controls, and computing to train these large language models versus more open source development? How do you think about that balance? Again, if we're going to stay in the lead, we have to figure out the right balance here.
Well, I think if you look at the history of software, you find that export controls have never worked because software is easy to copy, easy to transport. And so if you're going to try to control software or control model weights, which is just a file one can email, I don't think that's going to work. Could you try it on the margin? Maybe you could, but I would not bet on that as a long-term competitive strategy. When it comes to machinery, I think we've got empirical differences. So for example, the company that makes the machines that can lay down thin films of materials as thin as 4 atoms thick, they invented those machines 50 years ago. They've been the dominant player for the last 50 years. And so I think in an industry like that, with a almost monopolistic structure, with deep competitive moats that we know because we can look at the last 50 years, if you were to tell me there's a sphere where if you control the tool, it will not be easy to replicate, I would say that sounds a lot more compelling. And so I'm much more sympathetic to trying to control things that are in the physical world because I think you've got a better chance of controlling things that are in the physical world, whereas anything that's on a file, that can be copied and pasted, I think your likelihood of controlling is low. And so in AI, there's a debate about closed weight and open weight models and whether you should control open weights. And it's a reasonable debate to have, but I think there's a huge question of efficacy. Suppose you want to control, will it work? And I think we have to be pretty skeptical that it'll work in the long run. However, if you look at the chip making tools and ask what progress has China made on its own lithography ecosystem in the now 7 years since the US has been pressuring the Netherlands not to sell the most advanced tools to China, it's not obvious there's a lot of progress. There's certain types of tools where China's market share is growing in the domestic ecosystem, but we've yet to see in a real manufacturing facility a Chinese lithography tool anywhere close, not the cutting edge, anywhere close to the mid-range. And it's been 7 years. And so I think that's a sphere where I got a lot more confidence that controls are going to be durable in the long run because they've already been durable for 7 years and arguably for decades if you look at these companies' competitive position.
That's great. I just want to remind everybody there is an email address up here. So if you have questions for Chris, please send them to that email address, and we are tracking. Actually, one question did come up from the audience. So what size CHIPS Act would be needed to have an impact? You talked about the investment, I think, of $80 billion. It was like twice what the CHIPS Act was. And related, what will happen with the Biden CHIPS Act projects?
So the CHIPS Act set aside $39 billion by Congress to provide grants for chip-making facilities, which in almost any other sphere of life is a gargantuan sum of money. TSMC last year spent around $35 billion in its own capital expenditure. And the CHIPS Act wasn't 1 year, it was for a half-decade-long set of investments. And so through the CHIPS Act, we're going to be spending much less than TSMC on its own spends each year for the next half-decade. And so that helps you understand the scale of the funds that you would need to really begin to shift supply chains. And the dilemma the US faces is this: we're not sure what's going to happen in the Taiwan Straits. It could be very bad, or it could be an uncomfortable status quo that persists for 1 year or 2 years, or maybe even 10 years. And so we've got to make investments considering that uncertainty. And if you were to say, I'm sure something's going to go wrong next year, then I would gladly sign up to $1 trillion of investment to solve that problem. But we're not sure. And so that's the uncertainty that forces us to modulate how much we spend. I think if you look at the current administration, what we've heard thus far is the president vocally criticize the CHIPS Act, but we also see in Congress deep bipartisan support from very senior Republicans and Democrats for the CHIPS Act. And if you ask yourself, what's a better idea for solving the Taiwan dilemma? I think it's not clear there is one. We tried tariffs for 12 hours yesterday. I think there's no doubt that tariffs incentivize domestic manufacturing on the demand side, but it's also the case that for 12 hours yesterday, there was a $100 million tariff on the importation of extreme ultraviolet lithography tools from the Netherlands. $350 million times 25% from the Netherlands. That is a mind-boggling increase in the price of making a chip fab. And so if we're going to do the tariff route, we've got to be smart about it, because taxing importation of tools needed to make chips that are produced by one company in the world that happens to be in the Netherlands is not a way to make more chips domestically.
So Chris, you've mentioned the importance of supply chain several times. I've been listening, and you've talked about it a lot. So who, if anyone, manages the supply chain? from software to wafers, transistors to the machines. So is Taiwan, is the Taiwan company doing that? Who is it that manages the supply chain?
The challenge is that the answer is no one. No one manages it, and no one really could manage it all. Going from all the way down to the basic materials, all the way up to the chatbots using AI systems. It's too complicated. When I started studying the chip industry, I was sure I would find the person who understood the industry. And I started doing interviews and realized there were a lot of people who understood one level up and one level down, but you just couldn't be an expert in everything. And that is on the one hand, a source of resilience, because you have distributed expertise trying to solve each segment of the problem separately. But on the other hand, when you've got solely commercial considerations driving that, you end up with decisions collectively being made that are rational for businesses, at least in the short run, but irrational for the country. And that's what's happened with Taiwan. I love the Taiwanese. I have great respect for TSMC. I was there a couple weeks ago. I know them very well. I wish them the best. It is crazy to have 90% of the world's advanced chip making in one country, right off the coast of China. And no one was asking themselves the question, is this a good idea, until it was too late.
So you talked a little bit about what U.S. strategy would be, past and current administration. So during the Cold War, U.S. chip sanctions on the USSR led to more aggressive theoretical research and numerical analysis to compensate for that. And there are concerns that chip sanctions might inadvertently do the same thing. It might create an incentive, not only for Chinese chip innovation, but for algorithmic advances that may surpass the US labs. So how do you think about sanctions and their effectiveness?
I think that the question is, if there were no controls in place, would there be a greater or lesser incentive for algorithmic innovations? And when I talk to companies outside of China that are building big AI systems and spending billions or tens of billions of dollars a year buying advanced chips, if you listen to OpenAI, for example, they very acutely experience the cost of their computing power. They have to raise $30 billion once a quarter to build their next data center. I mean, it's a mind-boggling sum of money they have to spend on computing power. And so the thesis that Western firms that don't have controls don't face huge pressure for algorithmic innovation is just not true. And data point on that, if you look at pre-DeepSeek, the cost declines in serving AI systems, they were falling on the same trajectory pre-DeepSeek, not because of controls or politics, but because if you drive down the cost, your business model looks much more attractive. You can provide more AI services and get more AI customers. So I think it's true that Chinese firms have an incentive for algorithmic efficiencies, but I think so do US firms because the cost is just so high. And I don't see the evidence that the controls add a meaningful increment to the impetus that's already there to find efficiencies.
Yeah. So you mentioned a second ago about the fact that you had visited Taiwan. You deeply respect the fact that they have created this incredible capability, but that you think it's, I forget your words, but crazy to have all of this capability on one small island in that part of the world. So does encouraging a diversification of that manufacturing monopoly by bringing, say, more small chip manufacturers to the US, in a way, does it possibly increase the risk of challenges in the place that you talked about, which is the Taiwan Strait?
I think it's hard to game out with specificity exactly what's going to drive both Chinese and Taiwanese decision-making. Right now, we know that TSMC has one plant operational in Arizona, small plant, but nevertheless a good sign. There's several more that have been promised down the road. But even if these plants, all 6 of them, are built very rapidly, it's still a small share of TSMC's overall production and a small share of Taiwan's overall production. So in the sort of best case scenario for the US, there's 20 or maybe 30% of TSMC's production offshore and 70% onshore in Taiwan, which means that the cost to the world, including China, of knocking it offline is still very high, even if some of it is offshore. What I actually worry about more is not Taiwan dynamics, but China dynamics. China, as I mentioned, is racing forward towards self-sufficiency in chip making. It can't do the cutting edge, but it's getting closer and closer with everything else, with the low-end chips it needs for its industrial base, even with mid-range chips for consumer electronics. And I showed some of the charts of spending on these more mature manufacturing processes, and it's outstripping spending everywhere else in the world, almost everywhere else in the world combined. And so I think that China is going to be much more self-sufficient by 2030 than it is today. And if you ask yourself, what's the primary source of economic shock if something goes wrong in the Taiwan Straits for China? I think the answer is almost certainly chips. It's the #1 product that China imports. It's a product that they can't ramp up production of in the short run. Of course, you'd have a deficit of oil too, but you just tell people to drive less, and that's a much more solvable problem than finding alternative sources of supply for your chips. So I don't think we worry nearly enough about the implications of increased Chinese self-sufficiency for Chinese decision-making in and around Taiwan. And that's the dynamic that I think we should be following even more closely.
So I have a question that kind of goes to taking a reactive versus a proactive approach. So I think it was last summer, I was reading about kind of increased activity in the Taiwan Strait, Chinese doing military exercises and the like. And that clearly increased the urgency for the US and others to think about this issue in semiconductor manufacturing. And it was about that time that I started seeing the announcement in the newspaper about plants that were being planned. But of course, it takes a while to build a plant, and you spoke to that earlier. How are we caught off guard about that, or do you look at it that way? How is it that we're just now talking about this? Your book came out 2022, but clearly this didn't happen overnight. So what did we miss?
I think the key challenge has been that there are plenty of folks in the national security community who look at our dependence in Taiwan and say this is an enormous problem. But the key buyers of chips are not the national security community. It's Apple, NVIDIA, AMD, Qualcomm, companies that make smartphones or PCs or data center chips. And for them, risk around Taiwan is something that they acknowledge exists. They almost invariably have a much lower estimate of the risk than my friends in the national security community, but they acknowledge the risk is there. But they've got an alternative risk, which is that if they don't get their products to market the fastest, with the best battery life, the best computing capabilities at the lowest cost next year, then they're going to lose market share perhaps dramatically. And so if you're NVIDIA and you're getting calls from people like Sam Altman and Satya Nadella and the world's technology leaders saying, I want 100,000 of those immediately, you've got two choices. Produce them at TSMC, or say, no, I'll get them to you in 4 years once Arizona's up and running. And the answer from a commercial sense is obvious. And it's that mismatch between the people who are actually buying chips at volume and the perception of risk, both commercial and security risk, that has led the national security community, despite talking about this issue for some time, having made a lot less progress than I think it would have liked.
When you showed the chart where you asked everybody that fell asleep when you start talking about supply chains to bear with you for 30 seconds, certainly recognize the countries that were listed there. But there were a lot of countries that were absent that were surprising. So the UAE and Saudi Arabia weren't on that chart as far as we could see. Where do they fit into the supply chain discussion? Is that something they're developing the capability to contribute to? How do they fit into the picture?
They would both very much like to, both at the level of manufacturing chips and at the level of deploying AI data centers. And I think this is a real fascinating national security as well as an economic dilemma for the United States. There's no doubt that there's lots of money in the UAE and in Saudi Arabia. And there's no doubt that if you want to build a chip fab, it costs $20 billion. If you want to build an AI data center, it costs lots of money as well. And so both of those countries have been deploying money very actively over the last couple of years with the aim not just of making smart investments, but also of trying to attract investment to the Emirates or to Saudi. And there's been plenty of public discussion of, for example, the UAE's efforts to get TSMC to build a cutting-edge chip plant in the United Arab Emirates. And if you think there's concerns about permitting problems in Arizona or high tax rates, none of that exists in the UAE. And anyway, they'll pay for it all. And so if you're a company, getting a free check and no regulatory problems sounds pretty attractive. Same thing for AI data centers. A lot of energy in the Middle East, lots of sunshine for solar power. Anyway, they'll pay for most of it. So why don't you build your data center in the Middle East? The challenge is that I think it's not in our interest to have our most advanced AI capabilities being developed or being deployed at scale, or our chips being manufactured in either of those countries. Both because I think we should feel much more comfortable if it's mostly happening here, and because both of those are complicated partners, to say the least, and have been very active in trying to play us and China off one another over the past several years and have deep and uncomfortable and complicated ties with sort of who's who's of Chinese tech firms, including Huawei and the Beijing Genomics Institute, BJI. And so I think there are really serious concerns about what level of technology ought we be willing to share at what scale with our partners in the Middle East. And I think the US government's been right to tap the brakes on some of the investments that private sector firms would like to make. I think there's still work to be done here. I hear on a regular basis AI startups raising the next round of fundraising, getting a very large check from a Middle Eastern country saying, we'd really like to fund your technology with just one caveat. Can you move half your team to the Middle East? And I think that is a real challenge. We want their investment for sure, but we've got to have the right guardrails around what they can demand in exchange.
So we've been talking a lot about AI at this summit. We heard earlier, of course, that AI doesn't exist in a vacuum. And so there are other emerging technologies like quantum, for instance. So is there in the development of functional quantum, does that mean something for the chip supply chain? Is that a difference maker that you are thinking about? And if not, are there difference makers that would kind of change the calculus here?
You know, it's hard to make predictions about quantum because there's no trend line you can project. With the chip industry, I have very simple trend lines I can project all the way from the 1960s and with a fair amount of confidence tell you where things will be in 2 years. None of that exists in quantum. There's many different technological paradigms that are currently being tested. I think the one thing we can say with some degree of confidence is that many, if not most, of the paradigms that are being most actively explored commercially envision quantum not as a substitute, but as a complement for both AI-accelerated and traditional classical computing. And so if you listen to the big tech companies, Microsoft, Amazon, et cetera, they're envisioning you as a cloud computing customer having your traditional workloads, your AI-accelerated workloads, and your quantum workloads all next to each other. You're not going to replace the old, you're going to add layer new on top. And I think that's probably the right mental model for thinking about quantum, which means that the existing supply chain is not going to go away. We're just going to have a new supply chain to think about. We don't yet know what will be the key choke points in that supply chain.
Okay. Along those same lines, clearly these manufacturing processes and the equipment that achieve them are, I think in your words, some of mankind's most important achievements in manufacturing. But are there alternative strategies to achieving the ability to, for instance, develop latest generation AI? So there's a question here about the impact of small-scale defense manufacturing in the war in Ukraine, and the fact that it didn't take a 20-year program to develop a platform to make a difference in that conflict. There were the use of commercial, off-the-shelf, drone technologies, weaponized to the benefit of the Ukrainian people. And so is there a possible future where the same kind of idea, kind of nimble, agile manufacturing, distributed, could that kind of strategy be applied for chip manufacturing? Even if the chips aren't as exquisite as you very eloquently described, is there a future where you could get by maybe mass producing chips, maybe at a less, sort of precise level, but a level that would allow you to achieve your objectives in, say, AI?
I think there's a number of interesting projects, some startups that are trying to do exactly this, and I think there's a lot of promise for them. But I would say the lesson of the last several decades is that our appetite for processing power, not just in data centers, but in devices in our pockets, is unlimited. It's gargantuan. No matter how much money Apple charges for the next iPhone, people buy it. And you could have found people 10 years ago saying, iPhones are advanced enough. Well, empirically, that's not true, because every single year there's a better chip inside, giving you better battery life, letting you download more apps more rapidly, use increasing amounts of AI capabilities, and people want it. People want it. When it comes to autonomous systems, if you ask yourself, and the Ukrainians have done extraordinary things. I think they're in the early stages still of deploying genuinely autonomous systems. Battery life matters hugely. processing power is going to matter hugely. If you want to take in a ton of data, make sense of it right there, not need to access the cloud, you can be jammed in the process, the more processing power you have, the better decisions you're going to make. Simple as that. And I think the past several decades of consumer devices show us that pretty clearly. So I would not take a wager that we're not going to want more processing power in our devices. I think history suggests exactly the opposite. If they can give us more computing, we will find a use for it. And I think that's, if anything, even more true in an era of autonomous systems. I think that the second thing to note would be, there's been a lot made of Ukraine's efforts to build their own drone industry, and it's been extraordinarily impressive. I think it's also critical to note that they have assembled millions of drones using Chinese supply chains. And thankfully, China hasn't really cut them off. China's talked about cutting them off, but hasn't done it. But the components are all from China. And if you ask yourself, why is DJI the world's most successful commercial drone company? It's partly about price, partly about the fact that they've had a chance to iterate over products for a long time. But I'm also told that one of the reasons why their drones are relatively, comparatively capable of withstanding certain types of jamming is because they design and produce their own chips. So the communications up and down from DJI drone are custom made using their own silicon. They've got the volume to do that. US drone companies don't. There's not a single US drone company, to my knowledge, that designs their own chips. And so when you think about what does an autonomous system require, I think we're going to be thinking more and more about what are the exquisite capabilities that we're going to want on that so it can do extraordinary things for us. And when I look at the lessons from Russia, Ukraine, to me it seems like we're in inning 1 of autonomy. And to get to inning 4 or inning 9, we're going to need a lot more computing power in those systems.
Yeah. So Chris, I was saying earlier that your book is fantastic, Chip Wars. My only complaint about it was that my wife enjoyed it so much that she wouldn't let me read it until she was completed with it. She found a lot of it interesting and surprising. What did you find anything surprising in the research? Clearly you've found a way to explain this complicated process and industry in a way that others haven't. Did you find anything surprising in that process?
Well, as someone who comes from a non-technical background, I found every twist and turn of the technology extraordinarily fascinating and surprising. The fact that any of this is possible is, I think, a real surprise. Who would have guessed in 1958, when the first chip was invented, that we would have chips with 20 billion transistors? I mean, it's just like a mind-boggling number. It was impossible to conceive. So the existence of the industry, I think, itself is surprising. I think the one analytical takeaway that I had was about supply chains. I would have been one of those people who, 10 years ago, someone said supply chain, and I pulled my phone out of my pocket. And I now realize that actually you can't understand power in the modern world without understanding supply chains. It's as simple as that. And I think we still don't do enough. Outside of specific courses in supply chain management, the rest of the world needs to think more about supply chains because they're so critically important, introducing both vulnerabilities and capabilities that we do well to spend more time understanding.
So Chris, I mean, it sounds like you may be working on a new book on supply chains. So, all kidding aside, are you working on a new book on supply chains or any other topic you want to kind of preview today?
No, not yet in any sort of active sense, but I do spend my time thinking about all of the supply chains that we have started talking about. Biotechnology supply chains, drone supply chains. The level of analysis we've done, I think, is still only scratching the surface of what we need to do to fully understand what our vulnerabilities are and what the capabilities that we might produce out of the supply chains actually might be.
That's terrific. Chris, really interesting, insightful. I'm still thinking about the ball of tin that's many orders of magnitude hotter than the surface of the sun. Still trying to wrap my mind around that. Just really appreciate your keynote and this incredible Q&A. So thank you. Please join me in thanking Chris Miller.